Okay. In the last night we had the first online office hour. So if I don't have any further interruption, then every week I will make online office hour every Tuesday night. So please visit if you have any question. Yes. Mm, so let's go to our next topic. So in the previous lecture, our last discussion about charge neutrality when we have dopants inside the silicon. So uh, instead of this extrinsic silicon, if we have intrinsic silicon, then we have no dopant at all. So therefore, there is no electron which can occupy the dopant state or impurity state. So in this case, the answer or the equation is simply given by this way: the number of positively charged particle P and number or density of negatively charged particle electron should be perfectly balanced. So when you have this kind of condition, then you have charge neutrality. However, now problem is when you introduce dopants inside your system, then it can introduce additional states. So here we see an EV, and now there can exist a certain state introduced by our impurities. So basically, this impurity is if it is a donor, then it is an atom like phosphorus or arsenic. So we treat it as this way. For example, this one is just regarded as positively charged or positively ionized core atom or positively ionized arsenic atom and one additional electron. So these one, all other electrons are too tightly connected to the atomic core, so we think that the other electrons are just bounded to this phosphorus or arsenic, but we assume that there is one electron which have some freedom to fill some other states. When we consider the ground level, then of course this last electron will occupy this position. But if this probability is not 100%, for example, let's assume that there is 1% of probability to occupy other points, other states. So now let's say this one takes this conduction band state instead of the original dopant state. Then what will happen? In this case, we must distinguish the donor density and actually the number or density of electrons occupying this ND state. So there is no perfect agreement between this one. This can be actually not identical. So we are talking about how probable our electrons, the last electron, occupy other states than this original dopant originated state. That is given by what? Given by this one. So once again, this ND, the donor density, that is corresponding to the density, volume density of our phosphorus ion or arsenic ion. This number is given when you have, for example, 10 to the 17 per cubic centimeter doping density. Then this number is just a given number because we are assuming that the number is given. So I'm just repeating the same word once again. But the last term shown here, the last term is related with the occupancy of our electron. So if our electron is occupying this way, this state, then this electron actually neutralize the dopant state. For example, let's say that there is a phosphorus atom ionized, so, and at the same level there is one electron occupying that dopant state. Then what is the charge, net charge of this state? So energetic donor state. So you can easily understand this is corresponding to a neutral situation. We are now talking about this way. But now instead of that, let's assume this case. Then this electron can be regarded as a part of our electron density. So now it is taken into account in this quantity, and now we have a reduced number smaller than ND. So when we have a look at only in this energy level, then we have charge imbalance. There is no neutrality. Actually this part is positively charged. So this equation, although looks quite simple, anyway it is showing this kind of understanding. Okay, we have 4 different contributions inside our system. One is hole, one is electrons, and these are related with our donor states, and this is just working as background doping density, positively ionized. And the only thing we have to be careful about our donor state is this occupancy of that state. Yes, good, but problem is, what is this f sub d, so distribution function of our donor states located at ED? That is the problem. And when you have a look at the textbook's equation, then you will immediately find that the expression is a little bit, seems to be weird. So please have a look at, oh sorry about that, I have made a mistake or typo here. We must following the Tower's book, we must add this subscript. Anyway, this is the f sub d. We still assuming the existence of a Fermi level. Yes, it's good. And if we just draw Fermi-Dirac distribution, then how can you write down? In this case, we will write down in this way. So KBT, and here we have E sub d because we are working with this E sub d energy level. So that will be the typical thing we can imagine for the occupation probability for ED state. But interestingly enough and strangely enough, here we have some coefficient, and it is given as just 1/2. This is usually called as degeneracy factor. So unfortunately for this donor states, this number is corresponding to 1/2 or half. However, if we consider an acceptor impurity, then actually this number is known to be not a half, but it is a quarter, depending on the polarity of our impurities. It can have different numbers. Yes, so many questions can be raised. Why do we have deviations from the original Fermi-Dirac distribution, and why do we have dependence on certain kind of impurity types? Why do we have half or a quarter for this degeneracy factor? So in my original lecture plan, so I wanted to introduce a long discussion about why we have to have this kind of slightly modified form. But I think that right now, today, just to skip this part, and if we have some time left, then let's discuss this topic once again. So we have still more than 1 hour, so let's cross our fingers to have some time for it. So now I'm asking you that although it is quite strange, but just to understand, f is given by some weird function shown here. Why do we have this degeneracy factor? For a while, just forget about it, and we will just accept this one. Then now we can solve this problem. So equation 2.17 can be solved. Why? Because in this case you can express the whole density as a function of Fermi level. Once you know the Fermi level, then you can understand the whole density. And also in the case of electrons, once you know the position of Fermi level, then you can understand, you can calculate the electron density. And how about this ND? ND is just dopant density. So if you have a certain dopant density, this number is given. And once again, this here you have another ND. It's okay. And now we have f sub d, distribution function, and it is given as this form. And once this energy level is given, the only unknown variable is entirely just E sub f. When we determine this E sub f, then everything means that hole density, electron density, and the electrons occupying these donor states can be accurately calculated. So what you can do is just try a number, 0 electron volt, 0.1 electron volt, and check whether this equality or this perfect balance is matched or not. If this is not the solution, then you can try once again, and eventually you will happen to be, so you will find this solution. Of course, this is not the usual way, but anyway, in principle, you can do that. Please understand the equation 2.17 just state we must have charge neutrality when we have quite a large system, macroscopic system, because if we don't have charge neutrality, then what will happen? Then that will generate quite a strong source of electric field, and that is not allowed by our environment. If you have, for example, if you have a cube which is a highly positively charged thing, then what will happen? It will attract so many electrons, and eventually electrons will come in here. Then it will be eventually neutralized. So for this kind of macroscopic system, charge imbalance is not allowed, and this charge neutrality can be just treated as one equation for Fermi level. So where do we have Fermi level? It can be solved by solving this equation 2.17. So how can you solve it? It is out of our scope in this course. So I just inserted our expressions for hole density and electron density, and this is just a combined thing, ND and its occupancy. So we will have 3 different terms. Please note that EC, EV, NV, NC, whatever, E sub D, all of these quantities can be determined by you. You have, since you have a certain material, so you know where EV, EC are located. And since you are solving that problem, you can treat this temperature 300 Kelvin or 77 or 400 whatever. So all of other quantities just can be regarded as a given number and unknown variable, this E sub F can be solved. That is the situation, in general situation. However, in many cases we adopt this kind of thing, approximation, for shallow donor impurities. Shallow here means that starting from EC, our donor levels are quite close. Yes, this is donor level, and we say that, oh, this is shallow. If you have certain states generated by your donor or impurity, and when this energetic difference is quite large, then you say that, oh, this is deep and this is shallow. Okay, so are you with me? So now we can say that in this case maybe this quantity EC minus EF and ED minus EF, they can be regarded as a similar magnitude. Because EC and ED are quite close, so we can think about this one. And for shallow donor impurities, then now for shallow donor impurities, this is regarded as a hole density. Hole density does not contribute at all. And how about this one? In this case, this component is really small, and this component is really small, but in this case this exponential function leaves alone, but it is compared with this 1 plus something. Yes, we may have to make a comparison between this and that, and in this case usually for shallow donor impurities it can be just neglected for low doping density. So now we are going to this approximated form. What happens? We just neglected hole density and we assume that all of our donor state are just empty. I mean that, please note that once again this third term is originated from ND minus ND, and it's a distribution function. So when we say that this is quite close to N sub D, what happens? So we are implicitly assuming that, okay, this FD is quite small. It means that actually donor state is almost empty, and our electron should occupy other states, not this shallow donor state, and it should go any other state. And where it goes to? Yes, it is going into this conduction level states. So that's the reason why we have more conduction band electrons than the intrinsic carrier density. So I hope that everybody in this room can understand this shallow donor approximations. Once we have this simplified expression, then it is easy to say that our E sub F can be simply given by donor density. So if we have a high donor density, then our Fermi level is approaching to the EC level. So now let's say that if we have a higher donor level, then our EF will located here, and if we have a lower donor level, then we will have this EF quite far from this conduction band minimum. This is related with electron density, and hole density of course can be obtained by this expression, because at equilibrium the product between electron density and hole density should give us this kind of square of intrinsic carrier density of constant value. Sounds good. Sounds good, but sometimes when you first study this one, then you must have this kind of question. I mean that. Well, now let's review our treatment up to now. So what we have done is like this: EC, here EV, and there is a certain state called as donor state. Let's call it this is ED. And please try to remember what we have done in today's lecture. We just introduced certain charge neutrality condition. So here we have electron, or and we considered the charges located at this ED level. My question is, as a newcomer in this field, you must feel something is a little bit weird, because when you treat your electron density, what you have done is just a little bit semi-classical expression. So you have used Maxwell-Boltzmann distribution function for your conduction band electron. And how about your hole density? Your hole density, when you calculate your hole density, you also made an approximation about the Boltzmann Fermi-Dirac distribution. So you adopt also Maxwell-Boltzmann distribution. And finally, how about your expression for this f sub d function? Did you introduce such kind of a Maxwell-Boltzmann distribution for considering this f sub d? Actually not. You did it quite rigorously following this way. So now we must ask ourselves why we are allowed to apply different statistics into the same problem. Here we have 3 different states, and for this guy and that guy we introduce approximation, and only for these states in the forbidden zone we have applied this kind of rigorous distribution function. So please think about why we are allowed to do that. Okay, so I want to ask you this question, this simple question. And now so now I think that this is the typical way we do in the textbook. So although we must solve equation 2.19, another equation related with the charge neutrality, but for shallow donor impurities, now we can assume the fully ionized donors. So now 100% of our ND impurities are fully ionized, and it contributes or positively charged particles. That is our common way. But in general we must solve equation 2.19. So now let's do it in this slide. Now let's assume that happen to be our donor states are not located quite shallow from our EC state. Now let's say that we have some capability to change the position, energetic position of our donor states. Of course this is not possible. So if you have a certain atomic species, then the energy level is given, but let's just assume that you can freely choose E sub d. Then let's have a look at what happens. I have used well-defined quantities, and for NC and NV I have used this number, so you know quite well. And now let's assume that you have 10 to the 17 per cubic centimeter. We must have some feelings about the number. Now when you have 10 to the 17, you must feel that this is not that high. This is this should be your feeling about the number 10 to the 17. 10 to the 17 per cubic centimeter, this is not negligible. However, this should be regarded as low, relatively low doping density. I wanted to ask you one other question. If you have 10 to the 16, what is your feeling about this dopant density? It should be it should be treated as almost negligible doping density. Okay. And how about your feeling about 10 to the 18? 18 is a little bit higher than 10 to the 17, but it is not sufficiently high to be used. So high doping density. So you know, everybody know that in our transistor we have highly doped region, and this 10 to the 18 is far lower than the doping density required for this one. However, if you are talking about the channel region, then it can be regarded as a reasonable number, so slightly high. And now when you go to 19, 10 to the 19, this is sufficiently too high for this channel region. However, still it is too low for our highly doped region. Finally, if you go to 10 to the 20, yes, this is the density, doping density for your highly doped region. So we must have some numbers like 2 over 5 for our doping densities. So please have a look at this number. So when we come back to our original discussion, the number I introduced here, 10 to the 17, is not that high. So we must say that, oh, we have made a relatively low doping, and just by our imagination, so we will just change the energy level measured from our conduction band level. So this is the result. This left figure just shows the location of Fermi level. Yes, this is the Fermi level. And what is this red line? It is just showing that slope 1 graphs. So this is corresponding to our just ED level, and this is EF level. So you can clearly find two different behaviors. What is two different behaviors? One is when you go to this way, then your dopant level and your Fermi level. In this case, your Fermi level is far below than your dopant level. So now you can say that, okay, now if we have EC and ED, and somewhere far away from this one, now we have E sub F. Yes, so then what you can see is, since the distance between EF and ED is quite high, so what will happen? Yes, FD will be quite close to 0, you know. So therefore our original donor states are almost completely empty, and all of these one move into this conduction band level. So that is the conventional situation we are considering for shallow impurities. However, if we go to this way, this energy range, what happens? In this case, actually Fermi level is even higher than our donor state. So simply speaking, now when we have a certain donor state, so let me just draw once again. When we have certain donor state, actually Fermi level is located even beyond it. So it means that for our donor states, so F sub D, the occupancy will be almost close to 1, and all of our last electron for our phosphorus atom or arsenic atom is just staying in nearby its core electron atomic core. So no ionization actually happens. So you can easily understand there is clear distinction between this and that. And you can see that the crossover point is located here, and this energy difference is about 0.2 electron volt. Then maybe you say that, okay, if we have an impurity whose level is within 0.2 electron volt scale, then maybe it can be used as an impurity. But no, actually it's not. So please have a look at this one. So in this case, for example, yes, so as you can easily understand, even when we have roughly 0.2 electron volt below the conduction band, then its ionization ratio is just 50% approximately. It means that although you have insert 10 to the 17 atomic core or impurity atoms into your silicon, but only half of it is ionized and half of it is just non-ionized. And so now let's come back to our very well-known graph shown. Oh, sorry about that. So I must open another one. Let's go to our, okay, this one. Now you can easily understand why these green shaded ones are working as a worst thing. So you can see that the numbers shown here, for example, iron or manganese or nickel, copper, zinc. So you can see these numbers are quite far from our conduction band. Okay, here for example, here we have a relatively close one, but it also introduces many unwanted deep states. And you know that once you have these deep states, and it cannot contribute to your conduction band electron or valence band hole. There is another story. So let's say that, okay, I understand the situation. So now some of you may say that, okay, I will just use only 50% of our dopants. I'm okay. And the remaining 5 times 10 to the 16, I will not use it. Why not? But point is, unfortunately, when you have this kind of deep state, something really bad happen. And that. So if you have, say, EC, once again EB, and let's say that you are now having some deep state, then now you understand only a small portion of electrons are locating here, so it is only partially ionized. So then what will happen? In this case, it has some states given by ND times 1 minus FD, which are not occupied. They are empty. So you know this is the density of empty states. If it is just kept, or if they are staying there without any changing in its occupancy, then everything will be quite happy. So I don't care, because although you are not ionized, if you don't touch the electrical performance, then I will not care. But point is, sometimes an unlucky electron is once again move into this donor state, and sometimes something once again go to this state. There can be, it is not that much frequent, but there are some occasions where our electrons are move or transit between the donor state and conduction band state. That makes a problem. So although you wanted to have a certain number of electrons, but this number of electron is not a constant. As time being, or as time elapses, some of your electron is once again captured by this deep state, and once again released from this electronic state. So it is this state, since it has some ability to capture your conduction band electrons for a while, and after some time later it releases it to once again to your conduction band. It is typically called as an electron trap. So that introduces quite a big problem, big trouble to you, because when you try to make your electronic device, you wanted to keep certain constant level of electronic current, but with the existence of this kind of deep state, sometimes your electrons are captured and released, captured and released, although you have applied the constant voltage to your device, but inside your system the number of electrons are fluctuating, and it introduces certain fluctuation of electronic current. That is actually the main cause of many problems. So why do you have many problems? So if you study further, then you will find the reason. But for a while, let's just assume that that is not a desirable case. So now let's come back to our main discussion. So when we solve charge neutrality equation, it is clear that only when we have sufficiently shallow donor levels, then it is fully ionized. And if we go to deep states, and the efficiency for ionization reduced quite drastically, so we must find out some species which is good for making shallow impurities. Okay, shallow impurity levels. So now you understand the situation, but there is another story. Now we have to consider behavior of so let me just draw once again. I'm again and again challenging your current understanding, present understanding on the doping, and if you feel something is strange, then please think about a little bit further. So up to now, what we have done is like this. Here we have EC, and we have a shallow trap state. Okay, this is ED, and there exists a Fermi level far away from our donor state. Yes, so please remember my argument. Since ED and EF are quite much separated in energetic term, so we are now saying that FD equal or quite close to 0. I told you that since F sub D is quite low, so all of our electrons, almost all of our electrons should move into this conduction band level. That was my argument. Sounds great, but now think about once again. Then I wanted to ask you once again about the Fermi-Dirac distribution at the conduction band. Is it close to 1? Actually not. It is actually the distribution function occupying in this conduction band state is unfortunately even lower than this already small quantity, because this will exponentially decrease. So I'm now saying that I have only 100 Korean won. So I'm almost no money. However, all of you have just each of you have 10 Korean won. That is the situation. These donor states say that I have really low probability to have electrons. However, all other conduction band states say that my probability is even lower than you, because although our energetic distance is not that high, but it is about 40 milli electron volt. So therefore you means that this guy have higher probability to have electrons. So why that happen? Why we can say electrons are actually occupying this conduction band stage whose probability density or whose occupancy is even lower than this donor state? You can understand in that way. Although I have 101 and each of you have 10 won, Korean won. However, since the number of students are much higher than number of instructors in this classroom, so if we just collect or distinguish the money given to an instructor and money given to entire students, then that will be quite much comparable. So simply speaking, although here we have a higher probability to occupy this donor state, however, think about this one. So sorry about that. I think that some of our lecture recording seems to be lost. So please, when you come back to your laboratory, please check whether our all of current lecture content is alive or not. But anyway, the main message I wanted to deliver is, so when we think about the ionization of a dopant, we must understand when a shallow state is considered. Here we have F sub D and here we have F sub D, and actually the distribution function for our trap state is slightly higher, 2 or 3 times higher. However, density of state for this entire conduction band and density of state for this donor states, they show much higher, more severe difference. That's the reason why our electrons are occupying this way. Once you understand this kind of hidden story, then it is obvious that if I introduce quite much comparable density of state, then what will happen? now say that let's just say that instead of 101, so now let's say that I have 1001. Then although there are many students and there is only one instructor, but the overall comparison will be won by the instructor. So simply speaking, when you increase your donor density, then the ratio of ionization will drop. So when your doping density becomes comparable to the effective density of state of your conduction band, then there is 50 and 50% of occupancy. That really happens. So please have a look at these graphs. So when you have relatively low doping density, then almost 100% of your dopant atoms are ionized. However, when you go to the numbers like 10 to the 17, for example, then it becomes just 95%. Yes. So, but in this case, you can still assume the full ionization. But point is, now when you go to 18 or 19, please note that 19 or 18, that is related with the effective density of state of the silicon conduction band. That is given by 2.8 times 10 to the 19. So when it becomes comparable to the effective dose, then now the ionization rate drops down. Then if we just follow this expression, then now think about the extreme case. Extreme case means that here we have EC and it has effective conduction, effective density of state NC. And let's say that here we have just about 40 milli-electron volt energetic spacing, but now our doping density is like given 10 to the 20, for example, or even 10 to the 21. Then what will happen? If we just keep this argument, then and when we compared with the effective dose, our doping density is even higher, and F sub D and F sub D, this one is a relatively small number and this is a relatively higher number, so almost all of our electrons will occupy just donor state. So if we follow this way, then it goes down and eventually go to the number 0. That is typical thing we can imagine. However, experimentally, we have different behavior. So please look at this drop can be regarded as just increased density of state or increased density of doping density. But here we have once again recover of impurity, ionization rate, and eventually when you go to, for example, 10 to the 20, almost 100% of our electrons are once again ionized. So why do we have such kind of unexpected behavior? That is explained in this right figure. So let me just get it. Here you have symbols, and symbols are experimental data, and you have also solid line. Solid line is just obtained from a model. So, well, since model matches our experimental data quite well, so anything is just okay. So you know that this is energy. This axis is energy, and this is given as density of states. And yes, here you have density like 1.8 times 10 to the 18. So where can you find this number? This number is corresponding to somewhere around here. In this case, please have a look at this one. This state is originated from your donors, and here you have your conduction band. They are clearly separated. So donor states are well separated from the conduction band state, and these do not contribute to the electrical conduction. But point is, if you increase doping density and doping density and doping density, what happens? Actually, for relatively low doping density, there were clearly separated donor states. But when you go to high doping density, then what happens? Now your donor states are just merged into your conduction band. So there is no other state. So that's the reason why now we have almost 100% ionization in this case. So please have a look at this one. This is so when we have a sufficiently low ionization ratio, then we say that it is incomplete dopant ionization. So the incomplete dopant ionization is simply related with high doping density. However, if we have so high doping density, then actually donor states and conduction band states are merged into one body. So we have no such problem. And another way to reduce or another way to have relatively low dopant ionization is just to freeze out. Temperature is reduced. So please think about this one. Let's come back. Okay, when we have this diagram, so conduction band is much higher density of state, and our doping density ND is relatively small compared with this one. So also, since energy difference is just about 40 milli electron volt, so FD shown here and FD shown here has just 2 or 3 times difference in its magnitude. So this small distance was compensated by this much higher effective density of state. That was the situation. But I think that if you have studied well, then you feel that 40 milli electron volt is just less than 2 times summer energy. So its ratio is not that high. So exponential, we must care about some numbers like 40 milli electron volt over our summer voltage, summer energy. This is an important factor. But point is, this 25.85 milli electron volt is only valid at 300 Kelvin. If we go to, for example, 77 Kelvin, then what happens? Actually, this 77 Kelvin is liquid nitrogen temperature. So this is just a quarter of our usual temperature 300 Kelvin. So simply speaking, previously this number was just about 1.5 of our summer energy, but now when we go to 77 Kelvin, then this factor goes to just number 6. Then what does it mean? Actually, the difference between, where can I find, okay, the difference between this F and this F becomes even more severe. So simply speaking, when we cool down our semiconductor material, then effectiveness of our dopant drops down. So it is called as freeze out. Since temperature becomes too low, even the shallow dopant levels have no sufficient energy to push its electron into the conduction band. That is the dopant freeze out case. That happens in low temperature. So please have a look at this graph. So there are two different graphs, but anything is just okay. Think about these different colors. Black color is corresponding to 300 Kelvin, and go to the low temperature 200 and 150 and 4 Kelvin. Then what happens? Even for this low doping density, the ionization ratio drops down. It is simply because the energy difference between your donor level and conduction band is just fixed as a given number, and when your device goes down, cool down, then distribution function too severely, too rapidly decrease. So that is the case for your system. So now you may understand, when you have such kind of a device working perfectly at 300 Kelvin, and when you cool it down, then actually your previous assumption that 100% ionization, so there are tons of electrons or something like that, that drastically fails. So that is the thing we must take care, because so actually when I studied this kind of thing, actually as an engineer, low temperature electronics was not that much important at that time, because all of our consumer electronics are working at 300 Kelvin or even higher temperature. For example, if you are working in automotive application, then your operation temperature is higher than 300 Kelvin, not lower than that. But the point is, nowadays we have really an important potential application of our electronics. What is it? That is quantum computing. When we have quantum computers, so quantum computer is related with very important component called as qubit, and it is operated in the range of milli-Kelvin energy scale, temperature scale. So we are not talking about this one. This guy is usually made by other specialists, but this one contains very delicate information, and it should be anyhow amplified and processed by surrounding electronics. So therefore, since this is located at just a few milli-Kelvin scale, our electronics devices should be also placed lower than 4 Kelvin or similar temperature range. So that's the reason why In order to realize the quantum computing in future, not only this qubit technology, but also electronics technology should be adjust themselves to this low temperature application. So therefore you can nowadays find tons of discussion about low temperature electronics called as a cryogenic temperature electronics. Okay, so now let's go to, oh yes, so this fortunately this is the end of our discussion about equilibrium density of equilibrium statistics. So yes, we have done it, and now it's time to start drift. So now we are talking about the situation electrons are moving in net sum. So today we will talk about drift, and next lecture we will talk about other mechanisms. Everybody know diffusion. Today we will restrict ourselves to only to drift. And so unfortunately we are still missing this discussion about why do we have a degeneracy factor in our dopant distribution function, but let's cross fingers, later somehow we can treat this topic. So now let's go to the drift. So everybody know that the contents I will cover right from now on is related with electric field. So we are now saying that at equilibrium we can certain number of electrons and certain number of holes occupying the conduction band and valence band. Actually, when we have a pure silicon, its density would be quite small, like 10 to the 10 per cubic centimeter, but intentionally by introducing certain dopant, actually we can control it. We can increase, for example, 10 to the 16, 10 to the 17, or even higher than 10 to the 20. So now let's say that we have some electrons occupying the conduction band state. Then they can move. They can move. Here move means that really that change its real space position. From one position it can move and go to the other position. So it can really move. However, now we understand it can move, but how fast it can move. So I can run, but very slow. So other quite young and fast guys run much faster than me. So I'm saying that although let's say there are some electrons are moving quite slowly, and let's say that there is only one electron moves quite fastly, then which one carries more electronic current? So there are two of them, and let's say that I have 101. Once again, I have 101, and my fellow professor also have 201, and we are just walking in the campus. Then it can be regarded as 201 is carried from one position to the other position. So if I have 101, money is moved from one position to other position. Yes. Then instead of a slow professor like me, so I will give it to you and ask you to learn. Then what will happen? Then although we have the same amount of money, but since his speed is much higher than me, so the movement of 101 is much faster. That is the situation. I mean that we are now talking about, instead of the movement of money, my pocket money or your pocket money, but we are talking about the movement of what? Movement of elementary charge. And fortunately, all of electrons are equal. I have minus q, and I have minus q, and even this guy have minus q. All of electrons have the same amount of charge. Then the remaining thing is, how fast is it? Depending on its speed, the degree of movement of this unit charge is quite much different. So let's say that if one electron does not move at all, then there is no net movement of charge. Even let's say that there are 10 to the 10 electrons, 100 billion electrons are there, and they do not move. And there is only one electron, and it is moving a speed of 10 to the 7 centimeter per second. Then please make a comparison between their carriage capability. All of them, although the number is quite excessive, however, since they do not move, there is no net movement of charge. However, since the number is quite small, but since it is moving, it carries the carrier. So now we understand. I think that this is really an important observation. The main application of our semiconductor devices are electronic devices. I mean that you do not use it for your nutrition, or you do not use it for example, your heating, but you use your semiconductor device usually to use as a electronic switch. So therefore, current conduction is most important property you have to care about your electronic device, semiconductor device. And in this case, your current has two building components. What is it? How many electrons are there? That is one. And how fast are they? We must ask these two questions to ourselves, and fortunately we have successfully done the first question. How many electrons are there? Simply speaking, if we have pure silicon, we have no electron, no hole. If we have doped silicon, and depending on that doping density, we have similar amount of electron or hole. That was our answer to the first question. And the next question is, how fast is it? We must answer this discussion or this question. And now let's go to this concept of drift. Drift is used to describe net movement of charge due to an electric field. So this is related with charged particle. Although we say that so since I'm an engineer related with the semiconductor engineering, to me this property seems to be quite much universal. However, please note that this is only related with the charged particle. If you have neutral particle and it is not affected by this electric field. For example, now think about this one. you have some water, and inside it you have ions and neutralized molecules, and you apply certain electric field, then what will happen? Your ions will be redistributed according to its charge. So positive ion, negative ions, they will be separated. However, if you have just a neutralized molecule and it does not respond to the electric field. Fortunately, in our case, our charge carriers are all charged. So electrons are negatively charged and holes are positively charged. So when you apply the electric field, they will react. But reaction is different. For example, electric field or vector field. So let's say that there is a pair of electron and hole at the same position. Then what will happen? If you apply this electric field, actually this electric field just describe the force felt by our positively charged particle. So since positively charged particle is the reference one, so when we have this direction of our electric field, then our holes will push it in that way. However, our electrons will be, on the other hand, attracted by that electric field. So now you can see that this one, the force felt by our electron is simply given by electric field multiplied by minus q. Here q is a positive number, absolute value, so it has different, actually the opposite direction. However, for holes, they have the same sign. So if you apply electric field that way, holes are moving that way, that is, or accelerated that way. Okay, now under a given electric field E, now we know the force exerted on an electron. Then since we know force, then from this one we can easily understand acceleration. Acceleration is nothing but just time derivative of our velocity. So now acceleration is given by force divided by the mass of our electron. So here you can see that m sub n, why we have m sub n, as we have studied up to now, electrons or holes inside the silicon crystal structure is not a free electron or free, there is no free hole, but anyway, this is not a free particle. So it can have an effective mass which is different from the rest mass of electrons. So this is an effective mass. So by solving this equation, F equal to ma, Newton's second law, we can easily understand this is the solution. Starting from the initial velocity, when we have a constant electric field for certain domain, then our electron velocity will be changed, linearly changed with time variation. Simply, let's say that one electron was just at rest, and now we apply this directional electric field. Then what will happen? It will be attracted by that way. And if it is located in a constant electric field, then it will be accelerated. After some time later, then it will gain quite a high velocity or high speed. That is described in this one. Then my final word is, if we just follow this expression, the solution of our Newton's second law, then when we go to t equal to infinity, then what will happen? Then according to this one, then we will have quite a high speed originated from this acceleration term. Indefinitely, we will have a super fast electron. However, everybody understand this is not the case. The speed of electrons inside the silicon is just limited to some values, and it does not approach to the speed of light. So why do we have this kind of the deviation from this simple Newton's second law? So we will discuss this topic in next Monday. Okay, thank you for your attention, and I want to